Good afternoon to all students. Today I am going to discuss the topic pile foundations. So we have two types of foundations. One is shallow foundation, another one is deep foundation. So according to Terzaghi, if the breadth of the footing is greater than depth of the footing is known as the foundation is known as shallow foundation. If the depth of the footing is more than the width of the footing or foundation is known as deep foundation. So, for example for deep foundation is pile foundation, copper dam foundation, Kaizen's foundations. So, these three are example for deep foundation. In deep foundation, the depth of the foundation is more than width of the foundation. So, today's topic is pile foundation. So, what is mean by pile foundation? So, pile is a structural member which transfers the load coming from superstructure to the hard strata through the weak soil. So a pile is a slender structural member made up of concrete, steel, wood, or composite material. So it may be made up of concrete or steel or wood, or it may be combination of one or two materials. So a pile is either driven into the soil or formed inside by excavating a borehole and filling it with concrete. That means a pile may be precast concrete or cast in situ. So a pile is manufactured at factories. It is transferred to site. It is known as precast pile. Suppose if the pile is manufactured at sites itself, it is called as cast in situ pile. So pile foundation is the type of deep foundation in which the loads are taken to a low level by means of a vertical members, which may be timber, concrete, steel. That means load is transferred from superstructure to hard stratum through timber piles, concrete piles, or steel piles. So where we need to go for pile foundations. So these are the situations where we need to go for pile foundations. So first one is the load of the superstructure is heavy and its distribution is uneven. Heavy, but distribution is uneven. Then second one is the topsoil has poor bearing capacity. So the topsoil has poor bearing capacity, it cannot take the loads. So that we need to go for pile foundations. So the subsoil water is high, so that pumping of water from the open trenches for the shallow foundation is difficult and uneconomical. So whenever the water table is at the ground level or near the ground level, so we dewatering it becomes difficult. That's why we need to go for deep foundations. Next, large fluctuation in subsoil water level. So that sometimes water table may be at the top level, sometimes water level may be decreased to significant depth. In such a situation, we can go for pile foundations. Next one is the structure is situated on seashore or riverbed where there is a danger of scouring action of water. So in the case of waterfront structures, so there is a danger of scouring action of water. So that we cannot go for shallow foundations or any other raft foundations. So that we need to go for pile foundations. So another situation is canal or deep drainage line exists near the foundation. So if the foundation is situated near the canal or deep drainage, so shallow foundations are not suitable because it will be submerged in water. That's why we need to go for pile foundations. So for foundation of transmission towers and offshore platforms which are subjected to uplift forces, because transmission towers and offshore platforms are situated in water, so that these structures are subjected to uplift forces. So in order to resist the uplift forces, we need to go for pile foundations. So these are the situations where we need to go for pile foundations. So scoring where the scoring action is predominant, so offshore platforms and transmission towers. So we need to adopt the pile foundations because shallow foundations or any other raft foundations are not suitable for such situations. So we have so many types of piles, but while selecting the pile, we need to keep in the mind. So a pile is selected based on these factors. So nature and type of structure, location, material, equipment and fund availability, type of soil and its properties, groundwater table, durability of pile, length and number of pile, case study of adjacent buildings, facility for pile driving, erosion of soil near structure. So while selecting a file, we need to keep in mind all these points. So each and every point is self-explanatory. So classification of files. So this classification of file is very important. This is a very important question for JNT examination. So mostly asked question in JNTU examination. Classification of files. So files are classified based on function, based on materials, based on method of installation. So based on function, files are classified as n-bearing file, friction file, compaction file, tension file, anchor file, fender file, batter file, and a sheet file. It is not better file, it is a batter file. So the first one is n-bearing file. So n-bearing file means the file which transfers the load through its bottom only, not skin friction. Not friction between the soil and pile. It transfers the load only by its bottom tip resistance, also called as tip resistance. So it will possible. So the pile transfers the load through its bottom only in the case of soft soils. In soft soils, there is no friction between the soil and pile. So the second component, friction component, is absent. So the pile transfers the load only through its bottom tip. So bottom are tips rest on hard strata. So the ultimate load carrying capacity equal to load resisted by bottom of the pile. Only bottom of the pile. So friction piles. Friction pile means the entire load is taken by the friction between soil and pile. So when weak stratum or compressible stratum exists to a large depth or greater depths, so it is not economical to extend the pile up to large depth. So piles are embedded only a few length in the soil mass. So in this case, the load applied on the pile is taken only by skin friction between the soil and the pile. So this situation exists in the case of loose soil extend to a greater depth. Piles are developed at depth when friction resistance developed equal to load. That means the load applied on the pile equal to friction developed between soil and pile. So total friction resistance can be increased by increasing the length and diameter, making pile surface rough, placing closely or grouping of the pile. So by these three uh, parameters affects the friction between the soil and pile. So these are increasing the length and diameter. If you increase the length and diameter, skin friction resistance also increases. The pile surface is rough. Friction between the pile and soil also increases. Placing closely or grouping of the piles. That means if the piles are grouped closely, then friction between the soil and pile also increases. So friction pile means the entire load is taken by friction between the soil and the pile only. So there is no tip resistance. There is no end bearing resistance. So these piles also known as floating piles because these piles are look like floating in soil. That's why it is called as floating piles also. So compaction piles. These piles do not carry any load. These piles do not carry any load. For increase, it is used to increase the bearing capacity of the soil by densifying the soil. So while pile driving, what will happen? While pile driving, the surrounding soil is densified so that the load carrying capacity of the pile soil also increase. These piles cannot take any loads. The purpose of the pile is it increases the density of the soil mass. By driving the pile with hammer blows, the surrounding soil may be densified. That is the main purpose of this compaction pile. The name itself indicates the pile which is used to compact the soil is known as compaction pile. Tension pile. So when structures subjected to uplift due to hydrostatic pressure or overturning movement, in such cases, the uplift force is resisted by using these tension piles. So in the case of piles, structures which are rested in water, so they are subjected to uplift force due to buoyancy effect. In such a case, piles are used to resist the uplift force. uh, exited by the water. Anchor piles. These provided anchorage against the horizontal pull from sheet pulling or any other pulling. Anchor piles. It anchors the ships or it anchors the any other structures. Fender piles. So these are used to protect waterfront structures against impact from ships or other floating objects. So if these piles are not there, what will happen? The ships may directly in contact with the structure, so that the structure may be damaged. So it is also asked in gate. So fender pile. Please remember, fender piles are used to protect the waterfront structures against impact from ships or other floating objects. These fender piles also known as dolphins. Please remember dolphins. Very important one more question. So butterfly. Butterfly means it is inclined, not vertical. Sometimes it may be vertical, sometimes it may be inclined. So these are used for resist large horizontal forces or inclined forces. It may be vertical or inclined. Butterflies. So the main purpose of butterfly is to resist large horizontal forces or inclined forces. Sheet piles. So they are used as bulkheads or impervious cutoff to reduce the seepage and uplift under hydraulic structures. So in the case of structures which are constructed in rivers, in order to divert the river, sheet piles are used. Sometimes in order to isolate a land within a ocean or within a river, sheet piles are used. So sheet piles are classified as concrete sheet piles, steel sheet piles, or timber sheet piles, depending upon the materials used. So classification based on pile material. So we will use different types of materials for the manufacturing of the pile. Depending upon the material, the pile is classified as concrete pile, steel pile, timber piles, composite pile, sand pile. So concrete piles means the piles which are constructed by means by using concrete, cement, concrete. Such piles are known as concrete piles. Concrete piles may be precast piles, cast in situ piles, pre-stressed concrete piles. So precast piles means they are manufactured at one place and transferred. After manufacturing, it is transferred to site, then it is driven into the ground. So cast in situ means a borehole is made inside. That borehole is filled with reinforcement and also concrete. So the pile which is made inside itself is known as cast in situ piles. The piles which are made at one place and transferred to another place, they are known as precast piles. So pre-stressed means in order to increase the tensile strength of the steel, sometimes the steel may be pre-stressed before the construction or after the construction. They are known as pre-stressed concretes. Precast concrete piles. So this over. Cast in situ also over. Steel piles. So the piles which are manufactured by using steel are known as steel piles. So commonly used steel piles are H piles, box piles, and tube piles. H piles. These piles are usually of wide flange section. They are suitable for terrestrial type structure in which pile extend above ground level and acts as a column. They have small cross section area, therefore they can be easily driven in the soil. So it is used as a long pile with high bearing capacity. Box piles. They are rectangular or octagonal in shape. It is filled with concrete. These piles are used when not possible to drive H piles into hard stratum. Tube piles. Tube piles are piles of steels are driven into the ground. So concrete is filled inside the tube piles. So because of circular cross section, tube piles are easy to handle and easy to drive in. So timber piles. These piles are prepared from trunks of trees. They may be circular or square. So diameter of the piles are 30 to 50 centimeters and a length not exceeding 20 times its top width. At bottom, a cast iron shoe is provided, and at the top, a steel plate is fixed. So for group of pile, each pile is brought at same level, and concrete place is provided to have a common platform. So composite piles means the pile is made up of more than one material. So this type of construction in which piles of two different materials are driven one over the other. They act together to perform the function of a single pile. So in this pile, advantage is taken of durability of concrete piles and the cheapest of timber pile. So timber pile is terminated just at the level of the groundwater table. Then concrete pile is extended to the grade depth. Sand piles. So these piles are formed by making a hole in the ground and filled with the sand and well rammed. The sand to be used should be moist at time of placing. The borehole diameter is usually 30 centimeters. Length of sand pile is kept about 12 times its diameter. The top of sand pile is filled with the concrete. Sand pile are placed at 2 to 3 meters spacing. Load test should be carried out determining the bearing capacity of the sand pile. So properly compacted sand pile can carry load up to 100 tons per meter square or more. So the next topic is estimation of pile capacity or load carrying capacity of the pile. So load carrying capacity of the pile or ultimate load carrying capacity of the pile is defined as the maximum load carried by the pile without failure is known as ultimate load carrying capacity of the pile. Safe load carrying capacity pile means ultimate load carrying capacity divided by factor of safety. So the maximum load carried by the soil without failure. So we should not design for ultimate load because we need to take some factor of safety. That's why safe load is different from ultimate load carrying capacity of the pile. So the maximum load carried by the pile without failure is known as ultimate load carrying capacity of the pile. Safe load carrying capacity of the pile means ultimate load carrying capacity divided by factor of safety. So estimation of ultimate load carrying capacity. So ultimate load carrying capacity of the pile may be determined by using the following methods: static methods, dynamic methods, penetration test, pile load test. So static method, by using static method, we can estimate the ultimate load carrying capacity of the pile in clayey soil, ultimate load carrying capacity of the pile in cohesionless soil, group capacity of the pile, and also we can find out negative skin friction. So here I am taking estimation of pile capacity by using static formula. So we have two types of soils. I am taking the first one, cohesive soil. So in the case of clayey soils, the ultimate load. So let us imagine it is a end bearing, both end bearing and friction pile. Both end bearing and friction pile. That means the load applied on the pile is taken by both tip resistance, end bearing resistance as well as skin friction. So ultimate load is equal to load carrying capacity at the bottom of the pile and skin friction between the pile and soil around the pile. So QE is equal to ultimate load carrying capacity. QB is known as end bearing resistance. QS is known as skin friction. So I am taking the first one, QB, end bearing resistance. So here QB means load. So load is equal to stress into area. So area means I am considering the end bearing resistance. So end bearing means bottom of the pile. Here we need to take the area of the bottom of the pile. So area at the bottom of the pile is equal to pi into diameter of the pile at bottom divided by 4. Pi d naught square by 4. Sorry, by pi db square by 4. db is known as diameter of the pile at the bottom. We need to consider only bottom of the pile. Sometimes the bottom of the pile may be enlarged. In uniform diameter pile, no problem. Sometimes the bottom of the pile may be enlarged. In such a case, we need to take the bottom of the pile, diameter of the bottom of the pile. So please remember, AB is known as area of the bottom of the pile, pi d square by 4, where DB is known as diameter of the pile at the bottom. So coming to FB, bearing capacity of the pile at the bottom of the pile. So here you can see that uniform diameter pile. So at top as well as bottom, same diameter. So the second one is enlarged base. At the base, the diameter is enlarged. So here AB is known as pi into dB square by 4, where dB is known as diameter of the pile at the bottom. Don't take D. You need to take the D suffix B. Diameter of the pile at the bottom. So the second term is FB, bearing capacity of the soil at the bottom of the pile. It is given by C into NC, where C is known as cohesion of the soil at the base. Please remember it is a N bearing resistance. That means the load carried by the bottom of the pile. So we need to consider the diameter of the pile at the bottom. At the same time, the cohesion also at the bottom of the pile. C is known as cohesion of the soil at the bottom of the pile. NC is known as bearing capacity factor. Bearing capacity factor is standard for clay soil. NC is equal to 9. Please remember, by default, you should be in your mind. It will not given in the problem. You don't have right to ask or write missing data. So NC is equal to 9. It is a standard one. For cohesionless soil, the value may be varies. It will be given in the problem. But for clay soils, NC is equal to 9. Please remember, bearing capacity factor for clay soil equal to 9. Don't forget it. So second term is skin friction resistance. QS equal to skin friction. Here also QS means load. Load is equal to stress into area. So area is known as surface area of the pile because skin friction exists between the pile surface. So that we need to take the surface area of the pile. So for circular one, surface area equal to pi d into L, circumference into throughout the length of the pile. So skin friction exists throughout the length of the pile. So circular pile surface area equal to pi into d into L. For square, perimeter equal to 4b into length of the pile. So for rectangular, 2 into length plus 2 into width into throughout the length of the pile. So please remember, AS is known as surface area of the pile. Fs equal to shear strength of the soil at the pile surface. So it is termed as average undrained cohesion. Average undrained cohesion or average shear strength of the soil at pile surface. Sometimes shear strength may be uniform or sometimes it may be zero top and varies linearly varies up to the bottom level. So we need to take here average undrained cohesion. So Fs equal to alpha into C, where alpha is known as shear mobilization factor. Simply it is called as adhesion factor. So alpha is equal to 1 for soft clay. For soft clay, it is assumed that complete contact of pile exists between the pile and soil. Complete contact. It is assumed that complete contact exists with pile and soil. So we will take alpha is equal to 1 for soft clay. So for stiff clay, it is assumed that partial contact of pile with the soil. So for stiff clay soils, there may be some gaps between the pile and soil. So there is no complete contact between the pile and soil. So that adhesion factor is taken as less than 1. So if it is stiff clay, adhesion factor will be given in the problem. Suppose it is a soft clay, so it is a standard value. Adhesion factor is equal to 1. So if in the problem if it is mentioned that it is a soft clay, then you need to take alpha is equal to 1. By default, you need to take alpha is equal to 1. It is a standard value. For a soft clay, alpha is equal to 1. So now coming to the first basic formula, ultimate load is equal to N bearing resistance plus skin friction. N bearing resistance is given by AB into FB plus AS into FS. So ultimate load is equal to area of the pile at the base equal to pi into dB square by 4. FB equal to bearing capacity of soil at the bottom of the pile. C into NC plus AS surface area of the pile. For circular, pi dl and average undrained shear strength equal to alpha into C. Suppose it is a square pile. The area of the pile at the base equal to B into B. Bearing capacity is C and C plus surface area equal to 4B into L into alpha into C. So ultimate load carrying capacity for rectangular pile equal to area, just area changes. B into length of the pile and perimeter equal to 2 into width of the pile and length of the pile. So average undrained shear strength equal to alpha into C. Bearing capacity at the bottom of the pile equal to C into NC. So after calculating the ultimate load carrying capacity, we need to find out the safe load. So safe load carrying capacity of the pile is equal to ultimate load carrying capacity divided by factor of safety. So QU is equal to QB plus QS. This formula is applicable for pile having combined end bearing and skin friction resistance such as sandy soils. In sandy soils, when load is applied on the pile, that load is shared by bottom of the pile as well as skin friction. If you take n-bearing piles, sometimes piles passes through water. In such cases, pile have only n-bearing. There is no skin friction because around the pile water exists. So there is no adhesion factor. So second term is negligible. In the case of soft clays also, skin resistance is negligible or ignored. So ultimate load carrying capacity of the pile is equal to n bearing resistance. So n bearing resistance is equal to area of the pile at the bottom into bearing capacity of the pile at the bottom. So for soft clays also, skin resistance is ignored. Second thing is friction piles. Sometimes hard stratum exists at greater depth. In such cases, pile cannot penetrate through the entire weak soil. Hence, the pile transfers through skin friction only. Such piles are called as floating piles or friction piles. So the depth is more. Hard stratum is situated at a greater depth, then the pile extends only some limited depth. In such a case, the pile is known as friction pile. The load applied on the pile is taken only by skin friction between the pile and soil. So ultimate load is equal to skin friction. So average undrained shear strength into surface area of the pile. Surface area of the pile is given by pi d into L into average undrained shear strength is given by alpha into C. So we have three modern problems in clay soils. The first one is uniform clay, pile extending in uniform clay. So you can see here the data is diameter of the pile equal to 30 centimeters, that means 0.3 meters. Unconfined compressive strength equal to 0.90 kg per centimeter square. Undrained cohesion is equal to half of the unconfined compressive strength. So 0.90 divided by 2 equal to 0.45 kg per centimeter square. So alpha adhesion factor already given in the problem. So it is equal to 0.70. So factor of safety equal to 3.0. So NC bearing capacity factor for clay soils, it is equal to 9. It may be given in the problem, it may not given in the problem, but by default you should substitute NC is equal to 9 in the case of clay soils. So here a pile is extending in a homogeneous soil, uniform clay deposit up to 6 meters. The diameter of the pile equal to 0.3 meters and other soil parameters are also given in the problem. We need to find out the load carrying capacity of the soil, load carrying capacity of the pile. So for clay soil, it is a circular pile. So in the problem it is given that it is a circular pile. So we have the formula QU is equal to pi d square by 4. D is known as diameter of the pile at the bottom equal to, it is a uniform diameter. The pile has uniform diameter. So 0.3 square by 4. So C value equal to 0.45. It is a kg per centimeter square. We need to convert it into meters. All dimensions should be in meters. So 0.45 into 10 power 4 into bearing capacity factor is equal to 9.0. Next pi diameter of the pile equal to 0.3. Length of the pile equal to 6 meters. Adhesion factor equal to 0.70 and cohesion equal to 0.45. So in order to convert it to meters, it is multiplied by 10 power 4. So ultimate load carrying capacity is equal to 20.675 tons. Safe load is equal to ultimate load carrying capacity divided by factor of safety. It is equal to 6.891 tons. So layered soils. So second model is layered soil. That means the properties of soil is changes. It is not uniform from top to bottom of the pile. So the cohesion at top equal to 50 kN per meter square, at middle cohesion equal to 65 kN per meter square, at the bottom of the pile cohesion equal to 55 kN per meter square. So the properties of soils are changes. So the remaining properties also given in the problem. The adhesion factor equal to 0.45, factor of safety is equal to 2.0, NC equal to 9.0. So we need to find out the ultimate load carrying capacity of the pile. Here in first term there is no change. In first term AB into CNC. AB means area of the pile at the bottom. At the bottom of the pile, the diameter equal to 0.5. So pi into 0.5 square divided by 4 into cohesion at the bottom. So first term refers to bottom of the pile. So C means cohesion at the bottom of the pile. C equal to 55 into NC. NC, if not given in the problem, assume it as a 9. Bearing capacity factor equal to 9. So there is no change in first term. But in second term, pi d into L into alpha into C. This is for friction component. Here according to length, the properties are changes. At the top 1.5 meters, cohesion is equal to 50. So middle 2 meters, cohesion is equal to 65. Bottom bottom of the pile, the cohesion equal to 55 kN per meter square. So we need to take separately. So for first 1 meter depth, pi into diameter of the pile equal to 0.5 into length pi into d into L, length equal to 1 meter into alpha equal to 0.45 into C equal to C at top, at part of 1 meter 50. So second middle depth, pi into diameter of the pile 0.5, length depth of the layer equal to 2 meters and 0.45 alpha equal to and C value equal to for middle layer C value equal to 65 kN per meter square. Next, third one, pi into diameter of the pile equal to 0.5 into length of the pile, depth of the layer equal to 3 meters into alpha equal to 0.45 into cohesion at the bottom layer equal to 55 kilonewton per meter square. So ultimate load is equal to 341 kilonewtons. Safe load is equal to ultimate load divided by factor of safety. 341 by 2 equal to 170 kilonewtons. So the second model is layered soils. First model is uniform clay deposit. That means pile extending in a uniform clay deposit. Model 2 is clay extending in layered soils. The soil properties are not uniform. The properties are changes with respect to depth. So when the properties changes with respect to depth, for each depth of the soil, we need to take separately the friction component. Next, model 3, variation of untrained shear strength throughout the pile. So here you can see the figure. Given data is diameter of the pile equal to 30 centimeters, 0.3 meters, length of the pile equal to 5 meters, top 1.5 meters is neglected. You can see in the problem, neglect the, see at the bottom of the problem, neglect the top 1.5 meter soil subjected to shrinkage. So top 1.5 meters is neglected. So the total length of the pile equal to 6.5, but we need to take only 5 meters because top 1.5 meters is subjected to swelling and shrinkage. So that layer should be ignored. So adhesion factor alpha equal to 0.3. So in this problem, a pile is extending up to 6.5 meters depth. Top 1.5 meters neglected. So we need to consider the bottom 5 meters. So here undrained cohesion changes 50 kilopascals at 1.5 meters to 180 kilopascals at 10 meters depth. With respect to ground level, if you take the ground level exactly at 1.5 meters depth, average undrained cohesion is equal to 50 kilopascals. As the depth increases, the cohesion also linearly varies. So at 10 meters from the ground level, the cohesion equal to 180 kilonewton per meter square. So here the ultimate load bearing capacity formula will not be changed. It is Same. AB into C and C plus AS into alpha into C. So AB is known as area of the file at the bottom of the file. Pi into diameter of the file at the bottom equal to 0.3. So pi d square by 4. So here question mark is C. Cohesion at the bottom of the file. So by using similar triangle concept, we need to find the cohesion at the bottom of the file. That means at 5 meters depth. That means at 6.5 meters depth from ground level, we need to find out the cohesion. So 50 kilopascal is uniform up to 6.5 meters depth. So from 50 kilopascals at 1.5 meters, it linearly varies. So at the top, take it is a 0. At 5 meters depth, it is 50 plus some x. 50 plus some x. So by using similar triangle concept, we need to find out the x value. So total depth from ground level is equal to 8.5 meters. Sorry, not from ground level, from 1.5 meters depth. So total from ground surface it is depth is 10 meters. Top 1.5 is neglected. So the entire length of this trapezium equal to 8.5 meters. So at top the cohesion, the undrained cohesion equal to 0. Then at bottom it is equal to 130. At bottom it is equal to 130. So 8.5 by 130 is equal to 5 by x. X is equal to 176.47. So 50 plus 76.47 will give the cohesion at the bottom of the file. So 130 is the cohesion at the bottom of the file. N is known as bearing capacity factor plus pi into AS is known as surface area of the file. Pi into D into L. Pi into diameter equal to 0.3, length of the file equal to 5 meters into pi D L into 0.3, adhesion factor equal to 0.3. Next, average undrained cohesion. So at the top, undrained cohesion is equal to 50. At the bottom of the file, undrained cohesion is equal to 130. So 50 plus 130 by 2 equal to, you will get 88. So by substituting all these values in this equation, we will get ultimate load carrying capacity is equal to 209 kilonewtons. So these three are the models in clay soil. Now coming to sandy soils. So estimation of pile capacity in sandy soil by using static formula. So the basic equation is same for clay soils and sandy soils. So ultimate load carrying capacity is equal to N bearing resistance plus friction between the soil and the pile. So ultimate load carrying capacity equal to pile tip resistance. Sum of pile tip resistance or end bearing capacity of the pile at bottom plus skin friction between the soil and the pile. So safe load carrying capacity of pile equal to ultimate load carrying capacity divided by factor of safety. So this basic equation is same for clay soils and sandy soils, but QB and QS may be changed for clay soils as well as sandy soils. So I am taking the first component, bearing capacity of the pile at its base. So bearing capacity of the pile at its base equal to bearing capacity of the soil at the bottom of the pile and area of the pile at the base. So already we know that area of the pile at the bottom equal to pi into d square by 4, where d is known as diameter of the pile at the bottom. So here question mark is bearing capacity of the shell of the pile at the bottom of the pile. So for cohesionless soil, bearing capacity is given by CNC plus gamma DF into NQ plus 0.3 into gamma B into N gamma. So for cohesionless soil, cohesion component equal to 0. For sandy soil, C is equal to 0. First term is option. At the same time, for pile foundations, width of the pile is negligible when compared to depth of the file, because depth of the file is more, width of the file is very small. So when compared to breadth of the file and depth of the file, breadth of the file is very small. So the the third term also negligible. So bearing capacity of the file at the bottom of the file is equal to only the middle one, gamma df into NQ, gamma DF into NQ. So QB equal to N bearing resistance, QB equal to stress in the area of the pilot bottom, FB equal to gamma DF into NQ, AB is known as area of the pile at the base, FB is known as bearing capacity at the bottom of the pile. So FB equal to gamma DF into NQ. So let us take the NQ. NQ is known as bearing capacity factor. For sandy soil, it will be given in the problem. It is not standard value. So, but for clay soils, NC is equal to 9. It is a standard value. So, coming to sigma V dash. Sigma V dash is equal to gamma DF into NQ. So, effective stress at the pile base level. Sigma V dash is known as effective stress at the pile base level. So, this sigma V dash depends upon critical depth. So, let us discuss what do you mean by critical depth. So, critical depth means, so if you take the effective stress distribution diagram, at the top of the ground, effective stress is equal to 0. So the depth increases, there is a linear increase in effective stress. So after reaching certain depth, effective stress becomes constant. So here critical depth is defined as it is a depth up to which there is a linear increase of vertical pressure. Beyond critical depth, the vertical depth remains constant. So the depth up to which there is a linear increase of vertical pressure. You can see in the figure DC, critical depth. The depth up to which there is a linear increase in vertical pressure is known as critical depth. So beyond critical depth, effective stress is constant. So critical depth will be given in the problem. Otherwise, we need to use this IS code formulas. So as per IS code formula, critical depth is given by DC equal to 15 into diameter of the pile for loose sand, DC equal to 20 into diameter of the pile for dense sand. So if it is mentioned that in the problem, for loose sand, take critical depth equal to 15 into diameter of the pile. Suppose if the product is mentioned that it is a dense sand, then critical depth take 20 into diameter of the pipe. So estimation of sigma V based on critical depth. So we will have two cases. One is the length of the pile is greater than critical depth. You can see here. Case 1. So critical depth is small, length of the pile is more. So in case 1, the sigma V dash equal to, we need to estimate the, we need to consider the effective stress up to critical depth only. So the length of the pile is greater than critical depth. The length of the pile is greater than critical depth. Sigma V dash equal to gamma dash into DC. We need to consider only critical depth. We should not consider the length of the pile. The case T is known as if the length of the pile is less than critical depth, less than or equal to critical depth. You can see the second case. Critical depth is more, length of the pile is less. So critical depth is more, length of the pile is less. So the length of the pile is less than or equal to critical depth. We should consider only the length of the pile. So if the length of the pile is less than or equal to critical depth, sigma V dash is equal to gamma ds TL. So please remember, if the pile length of the pile is greater than critical depth, consider effective stress up to critical depth only. The length of the pile is less than critical depth, estimate the effective stress up to length of the pile only. So gamma dash into DC, gamma dash into here. So this is the criteria that we should check while solving the problem. Please remember, if the length of the pile is greater than critical depth, sigma V dash equal to gamma dash into DC. So the length of the pile is less than or equal to critical depth, sigma V dash equal to gamma dash into L. So again coming to basic equation, ultimate load carrying capacity equal to QB plus QS. Estimation of skin friction between the soil and pile. So QS is equal to skin friction, pressure into area. AS is known as surface area. For circular pile, it is pi d into L. For square pile, it is 4b into L. For rectangular pile, it is 2 into length plus width of the pile into depth of the pile. 2L plus b into depth of the pile. Surface is known as shear strength of the soil at pile surface. It is given as K into sigma A dash into tan delta. So here you can see that delta is known as angle of friction between the pile and soil. Angle of friction between the pile and soil. So it is given in the problem. If it is not given in the problem, as per IS code, take delta is equal to angle of internal friction. K is known as lateral earth pressure coefficient. So there is a vertical pressure here. In order to convert the vertical pressure into horizontal pressure, we need to multiply it with the lateral earth pressure coefficient. So sigma A dash is known as average vertical pressure at the pile surface. So shear strength of the soil at pile surface equal to K into sigma A dash into tan delta. Delta is known as friction between the pile and soil. K is known as earth pressure coefficient. In order to convert the vertical pressure into horizontal pressure, we need to multiply the vertical pressure sigma A dash with the earth pressure coefficient. So K into sigma A dash into tan delta. So here calculation of sigma A dash is a question mark. So sigma A dash is known as average vertical pressure at the pile surface. Suppose if you take a top, sigma A dash equal to 0. So between 0 to 1 meter, average equal to top 0 at 1 meter depth, the cohesion equal to 40. So average equal to 0 plus 40 by 2 equal to 20. So between 0 to 5 meters, at 0, cohesion equal to 0. At 5 meters depth, cohesion equal to 60. So 0, average equal to 0 plus 60 by 2 equal to 30. So between 0 to 1 meter, at 0, cohesion equal to 0. At 10 meters depth, the cohesion equal to 60. So average equal to 0 plus 60 by 2. So suppose if you take in between 1 to 5 meters, at 1 meter, the average cohesion equal to 40. At 5 meters, the average cohesion equal to 60. So here we need to find out the average. 40 plus 60 by 2 equal to 50 kilopascals. So this is the basic equation. Ultimate load carrying capacity of the pile in sandy soil. AB into FB plus AS into FS. So QB plus PS. So AB is already we know that sigma V dash equal sigma V dash MQ is known as bearing capacity at the bottom of the pile. Sigma V dash is known as effective vertical pressure. It depends upon critical depth. NQ is known as bearing capacity factor. It varies for sandy soil, so it is given in the problem. So AS is known as surface area of the pile. K is known as earth pressure coefficient. Delta is known as friction between the soil and the pile. Sigma A dash is known as average vertical pressure. So allowable load or safe load is equal to ultimate load carrying capacity divided by factor of safety. So as per IS code, minimum factor of safety equal to 2.5. So in this case, we have two model problems. One is critical depth less than length of the pipe, critical depth more than length of the pipe. So I am taking the first one, model one. So for a pile driven in saturated loose sand. So here it is mentioned that it is a loose sand. For a pile driven in saturated loose sand, we need to estimate the ultimate load carrying capacity by static equation. So data is given in the problem. Gamma sat equal to 2 gram per cc, delta equal to 20 degrees, phi equal to 30 degrees, nq is equal to 18, k is equal to 1.2. So first we need to check the critical depth. So for loose sand, as per IS code, critical depth is equal to 15 into diameter of the pile. So 15 into diameter of the pile equal to 0.45. So 6.75. So critical depth equal to 6.75 meters. Length of the pile is given as 16 meters. So length of the pile equal to 16 meters. So 16 meters is greater than critical depth. So length of the pile is greater than critical depth. So here we need to consider effective stress up to critical depth only. So sigma v dash equal to gamma dash into critical depth. Gamma dash equal to gamma sat minus gamma W. So gamma sat equal to 2 gram per cc. Gamma W equal to 1 gram per cc, 2 minus 1. Critical depth equal to 6.75. So sigma V dash equal to 6.75 tons per meter square. So QU is equal to AB into sigma V dash into NQ. AB equal to area of the pile at the bottom of the pile. Area at the bottom of the pile. Pi into diameter of the pile equal to 0.45 pi d square by 4 plus sigma v dash equal to 6.75 into nq is equal to 18. 18 it is given in the problem. Next, so surface area A is equal to surface area. So here average equation changes so that we need to take two components. So one is up to critical depth. So pi into D 0.45 into length up to critical depth 6.75 into K 1.2 into average coefficient at top 0 at critical depth 6.75 0 plus 6.75 divided by 2 into tan 20 degrees. Next, beyond critical depth pi into D equal to 0.45 into length equal to 9.25 into K value 1.2. Next, average undrained cohesion. So at critical depth 6.75, beyond critical depth also 6.75. So 6.75 plus 6.75 divided by 2 into tan 20 degrees. So ultimate load carrying capacity of the pile equal to 71.94 tons. Allowable load is equal to ultimate load divided by factor of safety. So model 2, if the critical depth is greater than length of the pile. So for a pile driven in dense sand, it is a dense sand. So estimate the load carrying capacity from static equations. Use the following data. So gamma sat equal 22, diameter of pile 0.3 meters, length of the pile 5 meters, pi value 30 degrees, NQ equal to 18, K equal to 1.3, factor of safety equal to 2.0. So assume that water table is at the ground surface. So in sandy soils, first we need to check the critical depth. So for dense sand, as per IS code, critical depth equal to 20 into diameter of the pile. So 20 into diameter of the pile equal to 0.3 equal to 6 meters. So length of the pile equal to 5 meters. So critical depth 6 meters greater than length of the pile. So it is the second case. So we need to consider here depth, critical depth is more than length of the pile. So we need to estimate the effective vertical pressure up to length of the pipe. So sigma v dash equal to gamma dash in TL. Gamma dash equal to gamma sat minus gamma W. 22 minus 10 into length of the pile equal to 5. So 12 into 5 equal to 60 kN per meter square. So ultimate load is equal to AB. AB means area of the pile at the base. Pi into diameter of the pile at the base 0.3. So pi into 0.3 square by 4 into sigma V equal to 60 into NP is equal to 18. It is given in the problem. Bearing capacity factor plus we need to find out the average undrained cohesion up to length of the pile only. So pi into diameter of the pile equal to 0.3, length of the pile equal to 5 meters into K value equal to 1.3 into at top undrained cohesion equal to 0 plus at the bottom of the pile it is 60 kN per meter square. So 0 plus 60 by 2 into tan delta. So delta equal to 30 degrees. If it is not given in the problem, it is taken as pi value equal to delta. So tan delta equal to 30 degrees. We will get ultimate load is equal to 182.03 kilonewtons. Allowable load is equal to ultimate load divided by factor of safety. So 192 divided by 2.0. So 91 kilonewtons. So allowable load carrying capacity of the pile is equal to 91 kilonewtons. If you have any doubts, you can ask me. So tomorrow I'm going to discuss group capacity of the pile. మోనిషా మోనిషా 147
సార్
మన నీ డ్రైవ్లోకి వస్తుంది చూడు.
ఓకే సార్.
ఇది నాకు పంపించు, తర్వాత నేను రిక్వెస్ట్ పెడతాను యాక్సెస్కి, అప్పుడు నాకు యాక్సెస్ ఇవ్వాలి. ఓకే
ఓకే సార్.